one state. Right? What about this one? It will be 1, 0 state. What about this state? Again 1, 0 state. And this one 1, minus 1 state. These states I will call this kind of representation, which will be in the form of J and M. In this form. When they are in the form of J and M, I will call them coupled states. Clear? Uncoupled state, when they are in the individual J1 and M1, these are the uncoupled. They are coupling here. And when it is the coupled state, means it is the addition of the two. This one is the addition of the two. And this we call the coupling. Product states and coupled state. So the CG coefficients are actually the coefficients of the uncoupled product states. And we will now go on with them. Now I can write that any Jn state that I write, any Jm state. So this is a coupled state, right? This will be equal to summation on M1 and M2, and this will be equal to J1, M1, J2, M2, and multiplied with J1, M1, and J2, M2, right? Multiplied with Jn. Okay. I will explain this with analogies to the vector space, and then things will get clear to you more. If I do multiplication of these two, J1 and this R, so this is actually a unitary matrix, which you call the identity matrix. In vector space, you say that these are the unit vectors. When they are multiplied with each other, we will get 1. Like x unit vector dot x unit vector, y dot y unit vector, they will give you 1. And when these two are multiplied, they will give you the Clebsch-Gordan coefficients. Clear? When this is the coupled, and when the uncoupled are the product form is multiplied with this. So they will give you the CG coefficients. Let me explain this thing in terms of the vector space. You write vector R is x in x unit vector plus y in y unit vector plus z in z unit vector. Now R is actually the summation of all these terms, all these contributions. So you call R as the coupled vector, because there is coupling of x, y, and z components. This R is resembling to Jn. When I write this one is the coefficient along x unit vector. Right? This is the coefficient along x unit vector. For example, let me write this like this. That 2 in x plus 3 in y plus 1 in z component. Now what it will be? 2 is the coefficient along x, 3 is the coefficient along y, and 1 is the coefficient along z. If I want to take only one coefficient out of it, For example, I want to take the y coefficient out of it. So what I will do, I will make a dot product, which I call the inner product as well, and I will write this with vector, with the coupled state. Then this will give me the y coefficient. Clear? So when I multiply with the coupled, the product form here, this is from the product form, this is the basis. When I do multiply, I will get the coefficient of it. So it is like the vector space, we are dealing with this like this. So any state, any coupled state, for example, I now want to write the coupled state 1, 0. Is any coupled state, any vector, I can write in terms of x, y, z unit vectors with their corresponding coefficients. Clear? So any combination of a coupled state I can write in terms of the product states. Like I can write that, let's say I write 1, 0 state. Now 1, 0 state is C1 and up combination plus C2 and up down combination plus C3 and this is down up plus C4 and down down. Clear? Like these are the bases, these are the coefficients, these are the bases, these x, y, and z, and these are the coefficients. So any coupled form I can write in the form of uncoupled with their corresponding coefficients. C1, C2 is there are 4 states. So I have written 4 coefficients. These C1, C2, C3 and C4 are called the Clebsch-Gordan coefficients. Now how to find them? How to find them? If I want to find C1, it means I will apply with 2 up arrows this one. Then the up arrow with the up arrow, the inner product, the dot product of this will give you 1 and I will get C1. While C2, C3, C4, they will become 0. Just like here, y dot r. So only y remained here with this x and this z, it came out to be 0. Because these are orthogonal bases. Similarly, we are having these as orthogonal. Clear? So we will have to find out all these things one by one, and the representation is a bit different from your book because Griffiths is following Sn combination and Jm combination, not following the Jm combination. We will follow the Jm combination. Things are the same, right? One difference. The other difference is that when we write, when Griffiths write that 2 angular momenta, so S1, S2, so it is, the Griffiths is writing like S1, S2, M1, M2, writing like this. First writing the spin angular momenta, the quantum numbers, and then their orientation. While we will write it like this: S1, M1, S2, M2, right? We will write in this form. And then we can write, means this representation I can convert into J1, M1, J2, M2. Clear? So because the S I am writing in terms of J. Here I have proved that they are the same thing. So So we will go with this representation, while Griffiths is going with this representation. So that will be the difference with your book, but once you understood these things, then the representation doesn't matter. So we will go one by one here. Let's start from the thing here that I should erase this one in order to write some rules for understanding this table. Okay, so the very first rule is that the value J1 and J2 will tell you about the table, right? The value J1 and J2 will tell you about the table. If you look at the table of the Clebsch-Gordan coefficients, then on the top of it, here is written half into half, and some here will be written 1 into 1, some 3 by 2 into 1 by 2. Different values are there. So the J1, J2, which are written in the cross form here, it will tell us about the table, that which table we will have to follow. And here we are doing the example of J1 and J2 equal to 1 half, 1 half. So we are taking the table 1 half, 1 half. Clear? The second thing that we will be doing, this table is provided by the particle data group. And in the first view, it seems very difficult, but it is not difficult at all. The only difficulty here is that a lot of data is being put into one table. So the table looks a bit messy, but we will see that how this table can be worked out. The second thing, M1 and M2 will give you a given row. We are having the table, we are having the rows in this form. These are the rows. For the given M1 and M2 value, we will select a given row, while the third, the J and M value, the capital J and capital M values will give us a column. Right? The capital J, capital M will give us column. Like these are columns. 1, 1 column, then 1, 0 column, 0, 0 column, and so on. Clear? The fourth, if we will have given X value here, then that value means there is a separation, like 1, 0 column, and the value is 1 over 2 here. 1, 0 column, 1, 0, and the value is 1 over 2 here. So this 1 over 2 is actually the square root of this, like X, the square root of this. Why we are not writing square root on all of them? Because to write square root, it will take more space and the readings will become not clear. So in order to maintain the clarity in this table, we are skipping writing the square root symbol. And the other thing is, when minus comes in, then that minus we will consider out of the square root. Like for example, in this way we are having minus or here or here. If I will square root this one, then this minus will be out of the square root. Clear? So these are the 4 rules that I will apply on this table. And this will give us the idea of the table, that how we can work out this table. So we will have to start with this one, with the 1, 0. And 1, 0 I can write. Now we will have to consider first the J1 and J2, because we will have to first locate our table. And J1 and J2 in this examples are half half. So we will go to table half cross half, right? Then there is, we have located the table, and now our coupled state is 1, 0. So J and M, the coupled state. And we know that the capital J and M are actually giving us a column. So we will go to the 1, 0 column. Here is 1, 0 column. This one, 1, 0 column. And the 1, 0 column will give us the coefficient 1 over 2. But take square root of this. So it will be 1 over square root 2. Clear? It will give us, means we can square root this one. All values are square root form. So square root of 1 is 1, so doesn't matter. But here 1 over 2, it will be, the coefficients will come out to be 1 over 2. So I can write that 1, 0 is equal to 1 over square root 2, and then I will write J1 M1. So J1 is half while J2 is half. J1 is half, J2 is half from this representation. While M1 is half, right? M1 is half, and look here. For M1, 1, 0 column. So I will go to 1, 0 column, and the value is 1 over 2 square root. Clear? 1 over 2 square root. Now for M1 and M2, I will have to go to the row. So this is the row, right? So plus half and minus half are the values of M1 and M2. So plus half